Products are favored, and they cross, and what does favored mean? More of them. Okay, more react products. Does. What the heck's going on? Okay. And then value near 1. Equally favorable, and then approximately the same amounts of those at equilibrium. Okay, so everything from the K perspective, since it's called the equilibrium constant, it does mean at equilibrium. Because you can always start off with more or less of one or the other, and they're going to eventually react just until they're at equilibrium. Okay, so on the web quest, you guys got to part 1 on the second, all the way through part 1, you got to part 2. Part 2A, which is K expressions. I'm feeling like we're pretty good with that. You feel the same? I'm reading your mind. You feel okay with how to write a K expression, how to plug in values to a K expression, how to read a problem and pull the information out and put it in a K expression. The only thing I'm sure you're still shaking on is the ICE part of it, like plugging in ICE. Okay, but what about Le Chatelier's principle, where there were some things that were regarding shifting left and shifting right? All right, let me give you a little peek, and then we're going to go to our lab, which is an inquiry lab, which is going to let you see it, and then come to some conclusions about it, and then we'll recap together, because I think that moment of seeing it about yourself first will give me something to work from. Working from a blank slate is sometimes really hard. Okay, so I think that's going to be helpful. But what we have here is a situation where, let me just start fresh here. What we have, you know what, let's do this video first. I'm going to do it this way, and then we'll go from there. Did you please write down maybe 5 things you learned from this? 5 bullet points works for me. This can be the top, this can be on your notes, or this can be at the top of a new sheet for your lab. We're going to do our lab in 5 minutes.
Chatelier's principle, which explains what the system at equal.
All right.
In this lesson, you will learn about Le Chatelier's principle, which explains what a system at equilibrium does in response to stresses. Let's return to our original example of you digging a hole and your friend refilling.
Okay, so they just said Le Chatelier is referring to what? What a system does when you disrupt its equilibrium. Okay, so it's at equilibrium already, right? And then you're going to stress it out. What's a stress in your life? School. Okay, well, we have to go to school, so we can't really remove that stress. What's a stress that you have control over that you can remove or you can alter? People. For me, it's sleep. I get really grouchy, like the meanest person on the planet if I don't get 8 hours of sleep, which is most days of the week. Okay, literally. So I can accommodate and say, hey, my stress is not enough sleep. I'm going to bed at 8 o'clock tonight. Because that's going to be how I can alleviate that stress. A reaction can do the same thing. So it can make an alteration if it feels stressed. Well, at equilibrium, it's a happy place. It's got good chi. It's feeling great. But when you stress it out, it's going to have to accommodate by shifting to make more products or shifting to make more reactants. That's what the shift part means. And the stresses are a little different for reactions, right? We're not talking about sleep and people in school. We're talking about extra reactants, extra products, temperature changes, pressure and volume changes, things that affect reactions. So that's what this is going to start to go over.
Doing it simultaneously. If you start digging at a rate faster than refilling, the hole gets larger. In order to maintain a constant size of the hole, your friend must work harder to fill it faster. Following on the same idea, when a chemical system at equilibrium is stressed, the system works to restore equilibrium. This is Le Chatelier's principle. The stresses are changes to the concentration of either the reactants or products, changes to the pressure, although this is only applicable to gaseous systems, changes to the temperature. Let's examine a hypothetical reversible reaction at equilibrium where reactant A reacts with reactant B to form product C and product D. If we added more A and B, the system becomes stressed and is no longer at equilibrium. To counteract the stress, the system forms more C and D in order to remove the excess A and B. The equilibrium, therefore, shifts to the right. If we added...
So whenever you had the issue with too much A and B, too much reactant, what did they have to do? Don't say shift right. What did they have to do with these things, extras over here? When you say change them, what do you mean? Reacted them. Okay, so we took the reactants. We're like, react. We reacted them, and we made them react, and they formed what? Products. So since we forced the formation of products, forcing the formation of products means to shift towards the products, which means to shift right. It's just literally shifting right on the reaction. So the shifting right means that the equilibrium is just pushing forward towards the product formation versus the reactant formation.
More C and D in order to remove the excess A and B. The equilibrium, therefore, shifts to the right. If we added more C and D, the system becomes stressed and is also no longer at equilibrium. So to counteract the stress, the system forms more A and B. Therefore, the equilibrium shifts to the left. What happens if we remove C and D as they are being produced, or if the concentration of C and D is decreased? Please pause the lesson to think about this and resume when you are done.
What's going to happen?
The system is now stressed and no longer at equilibrium. To counteract the stress, more C and D are produced, so equilibrium shifts to the right. When concentration increases, equilibrium shifts to the opposite side of the reaction.
To consume it, right?
When concentration decreases, equilibrium shifts to the same side of the reaction.
To make more.
Changes in pressure.
Okay, last one.
The stress to a system at equilibrium is only applicable to gaseous systems. For this stress, we will examine another hypothetical reaction at equilibrium, where reactant A reacts with 2 moles of reactant B to form product C and product D. An increase in pressure means that there is a decrease in volume, so there is less space. Equilibrium will shift to the side of the reaction with fewer moles. In our example, an increase in pressure will cause equilibrium to shift to the right, since there are fewer moles. 2 moles compared to 3 moles on the left. A decrease in pressure means that there is an increase in volume.
Okay, so get out your box of air. I know you got it with you. Box of air. Increase your pressure. What happened to your volume? It went down. Okay, back up. Take your box of air, go back to normal. Increase your volume. Okay, what happened to your pressure? Why is it decreasing? There's more room, but what's literally causing that pressure? Like, what's causing pressure? Say again? So collision to the container wall, right? Okay, so remember, pressure is simply from collision to the container wall. So if you make more space, less collision to the container wall occur. We're on the right track here, right? So if my problem is, oh no, I've increased the volume, I've caused the pressure to go down. You have made this stress occur, which is low pressure. Your job is to reestablish equilibrium, which means get the pressure back up. Well, how do you get the pressure back up? You need more of what? You need more stuff in there, particles, to bounce around. Because the more particles you have, the more bouncing occurs, more collisions can occur. So if you find a direction in the reaction that has more moles on the other side, you're going to have to shift in that direction. And that's why they had 2 moles. Well, there it is. Okay. So in this reaction, it says all gaseous, right? How many moles of reactants are there? Count up your coefficients. Reactants. 3. 1, 2, 3. 3 moles of reactants here. How many moles of products? 2. Which side would have more collisions occurring? The reactants. So if your problem is I have too low pressure and you need to get the pressure back up, you have to find a way to get the pressure back up by increasing the number of collisions in the container wall. That has to be the side with more stuff. It's really an easy cause and effect relationship. It's just you got to figure out what was the problem, what was the stress. All right, so I'm gonna stop there for now. Let's do one from our worksheet from yesterday, which I don't have in front of me. You guys have your worksheet 1 through 6. We're gonna turn to the back side of that, and let's talk about shifting. Number 1, practice that case principle. And then we're going to go back into our lab. Who needs one of these worksheets from yesterday?
Well, I'm going to do that.
Here, I have your back. Okay, so on your worksheet from yesterday, you guys see that it says does it say H2? H2 plus Cl2 equilibrates. So when you want to say double hit arrow, just say equilibrates to 2HCl. Is that what it says? Okay.
Plus energy.
Oh, plus energy. Thank you. All right, the first example is increase in energy, temperature. Okay, if you increase temperature, what you're going to have to look for is, first of all, this thing is at equilibrium, right? It's got equilibrium arrows, it's at equilibrium. All right, it's at equilibrium, it's established in its happy place. What you're going to do is you're going to stress it out. But the stress has to affect this particular reaction. If the stress is not affecting this reaction, you just say no shift. Be careful, no shift, okay? So temperature, I don't directly see that here, but I can tell it's definitely related to energy, right? Temperature and energy, they're kind of the same thing. So if I've increased temperature, basically that means I'm increasing energy. So sometimes you got to read between the lines. Okay, so if you've increased energy, your stresses, and this is how I talk to myself about this. Oh no, I've got too much product. I've got too much energy. I need to get rid of this. How do I get rid of this? Do I shift left or shift right? Because you can only shift. You can only react in the reverse direction, which is what shift left means, or you can shift right, which is shifting towards the products or making more products. Do I want to make more products? No, because that means I'm going to make more energy, and that's just going to increase my problem. So I need to go which way? Left. I need to shift left. Shift left, SL. So if you shift left, basically what that means is that these products are going to be reacting with each other. They get consumed, and as they get consumed, reactants are made. Well, if they get consumed, it solves no problem. I had too much energy. When it consumes it, it lowers the energy. And that's it. Cool? Mm-hmm. Okay, let's do another one. What's the next one?
Decrease the volume.
Decrease the volume? All right, do you see volume in this reaction? No, right? You don't see volume. Nor do you think about pressure off the bat. But you need to always make that association between pressure and volume. And remember, these are gaseous, if it doesn't say so. Let's just make them all gases. Okay, so with this one, decreasing the volume does what to the pressure? Increases. So remember, this is an indirect relationship. Your box gets smaller, the pressure gets higher. Well, that basically just means, what about the particles? What are they doing? They're colliding like crazy with container walls. That's our problem. We need to fix our problem. Our problem is we have too many collisions in the container walls. Well, in this example, how many moles, so in this one we need to count moles of reactants versus products. How many moles of reactants are there? 2. There's 1 plus 1 is 2 moles. How many moles of product are there? 2 moles. Is either one of these sides, if you shift towards them, is either side going to alleviate our pressure problem? No. So if neither side will alleviate it, you put no shift. Now, let me make a hypothetical. Let's say, for example, this was a 3 here. Which shift direction would alleviate our pressure? Why? Because there's less moles, there's less bouncing, there's less pressure. So that domino effect, once you kind of see the problem, you can make a solution for it. You really do, I think you get it. I think you understand what you're talking about here. But let's do just 2 more just in case. What's the next thing? Increase?
Add HCl.
Add HCl? Okay. So what's our problem? What's our stress? There's too much HCl, which is a product. Okay, so yeah, you're deciding between reactions, products. So I've got too many products. What do I need to do? You need to react them, and when they react, yes, they shift left. They go backwards. So that's a shift left. The next one?
Add NaCl to the reaction.
Do you see NaCl in this reaction?
No.
Yeah. The reaction vessel is like the flask. It's just the container in which it exists in. Yeah, good point, because I was going to say that later on. Okay, so adding NaCl. Do you see NaCl in here?
No.
Do you see Na in here?
No.
Do you see Cl minus in here? You see it in a molecule form and a gas form, so that means that it's a little molecule. It cannot separate from the H to make H plus and Cl minus. If it were an aqueous form, yes, we would see that, and this could attack and actually cause the chloride ion to increase. It's called the common ion effect. It could cause that problem, but this is all gaseous. Nothing's going to react. Nothing's going to be added. This is as an inert substance, meaning it doesn't react with anything in equilibrium. So what do you guys think is going to do to the shifting? No shift. Last one.
Remove Cl from the vessel.
Okay, so if you remove Cl2, so chlorine gas, what's our problem? So there's not enough reactant. So what do I need to do to make more reactant? So the problem is I don't have enough reactant. You need to find a way to make more, so you shift towards it. So that would be, again, a shift left. Okay, let's look at our lab. Lab is in Cree lab. Solution A. I don't have a label. I have it back. I'll bring it around so you can have 2 large flasks of it. Solution A is a mixture that is at equilibrium. Guess what we're going to do to it? We're going to stress it out, okay? So we're going to stress it out by changing some reactants and products, temperature conditions, and so forth. So there's one set of equilibrium conditions you're going to go through with solution A, and you'll see those instructions. Most tables have most of the reagents that some of you guys might have to share between the 2 tables that are close by. The second equilibrium setup is potassium dichromate and potassium chromate, and it's a yellow and orange substance. They are carcinogenic. Be careful with them. What's carcinogenic mean? Causes cancer, but not like just on the spot. Okay, you're gonna have to look at it. It's just carcinogenic. They're more of our hazardous materials. You also have 1 molar hydrochloric acid and 1 molar sodium hydroxide. So they're in little dropper bottles. If you run out, please let me know. I might get you some more. But I'm gonna want you guys to make sure to record. Ooh, I printed out lab sheets for you. Yay. I want you to record your color changes. Everything for us, since we can't see the compounds themselves, we are really dependent on color changes. Nobody colorblind in here? I usually have like one person per year. Colorblind, okay. So if you cannot tell a color change, then you put no shift. If you can see a color change, putting down the colors that are associated with the reactants. So groups of 3, please go to the back. It's called the Chatelier Zinkery Lab. Chatelier Zinkery Lab. Gaggles. Oh, the below. Yeah.
Are you going to collect all of this, or are you just like... Do you have any 0.7 lead? 0.7 lead?
Can I look in a second? Thanks. Let's go. I'm going to stop you guys in about 45 minutes.
I guess that was clear, but
Thank you. Listen for me first. You have to find four test tubes, right? Five test tubes. I'm going to give you 10 milliliters of solution A, and you have to split it between four test tubes. So how many of these test tubes? 10 milliliters of solution A. What test tubes? How many five? First one is just make sure you read, of course. But I'm going to give you a tip. These little guys, I put clean, fresh, brand new, high best in your computer. You will see graduations on them. Do you see them? They say like 1, 2, 3. Use this to help you so that you're not wasting time with graduate syllabus. So you're going to use this, but wait, I'm not done. I'm bringing you 10 to 15 minutes right now. Make sure you get something for me that I can put that in. Other than that, please read, look at chemical labels so that you're not missing the wrong statements and such. Okay, have at it. It's just taking out water.
I said I wanted to try. No, I think you have Yeah. I mean, if we could. I know, I was right. No purpose necessary. I think we're doing something different. Alright, so we need 2.5. What's with the difference? Look at the size. If we blow something Last solution A.
That's not the one that's it's light brown. I'm gonna, you're
Alright, so Matt, you're gonna use that. Oh my God, that'd be the best.
Only two things are making shoes need more small plastic bottles to have stuff to do. Yeah, like even if you can still out, you can have eight sets. So we have normally small plastic bottles.
No, we tried to.
These solutions are fairly dilute, they're going to be a little difficult to see, so once you think it has changed, then stop. Once it has changed a little bit.
Reading. Want to separate.
Ready, guys?
Okay.
Ready, here we go.
Start recording. I know what
You're really.
Because I.
Oh, I was looking at it.
Are you guys done with this? Wait a minute, these are all way in there. We only have 2 options. We tried. Alright, we don't need.
Alright.
It's starting to reach the scale. This direction. Okay. Brandon Queen. Brett.
Now,
Guys, you need to rinse out your pipettes, rinse out your custard very well. And the drink of water.
that's the. Okay, hold on. No, sorry. No, I don't need to get. I still haven't do this.
It was the test too, correct? So basically, also, You stay. I don't care about All right, what are we doing next? All right, well, we've got two tests, right? How much you know? Is it two? No, I know what you want. All right, now, I'm really good for Wait. That would be. You'll be a super strong. All right. I didn't. All right.
Alright, get your attention real fast one more time. Any of the carcinogens, the potassium chromate and potassium dichromate, or the combinations of the acid base, I want this at the end in this flask and instead right here at the front. So this is the waste container that doesn't have to go. And once you see the color change, stop. Don't wait till you write it down and cover up.
It was in the neutral zone. It went to the other side. You're just gonna have to do it more. Five each. Just know something. This is three. All right. You don't know what you're doing. You see, we're definitely confused. We're just waiting. There's supplies, so yeah.
Repeat that time with us today.
I was waiting for that. It wasn't Lowry, it was Dave. And he wasn't even in the room. All right. Because I'm a pro.
Alright, get all your data collected in 5 minutes. All data collected in 5 minutes.
Okay, I hope you can. You have. Didn't have. You guys, exo the other right. Right. All right. I don't know where you're looking. You're reading correctly. Did you guys use some HCl?
All right, guys, I'll see you up here in a minute. Get all your stuff cleaned up, and I'll see you up here in a minute. I'm going to review this lab with you. Please be careful with your glassware. I hear it clinking. We're not having cheers. Thank you. All right, I'm starting without you guys in the back. Be quiet for me. Starting without you. You already got the first part ready, though, okay? So, equilibrium. We have this iron 3 thiocyanate and then iron 3 thiocyanate. Species added. What did you add to test tube 1? Was this the nothing one? I don't have my answer key for this. This was the nothing one. And so, observable color change NA, right? Not applicable to this one. And we'll skip that. What was test tube 2 you added? Okay, so the thing is here, we're looking for common ions or something that will react with the ions. So iron 3, you guys added FeCl3, so iron 3 chloride, that's not the species that's in common. What's the single species that's in common with this equilibrium? Fe3 plus. So you gotta say Fe3 plus in the form of iron 3 chloride, but it's the iron 3 that itself is the part that's important because that's the part that's in the equilibrium reaction. Observable color change, what happened? Orangey red. Okay, so I'm going to go reddish, but we all know it's shifting towards which way? Shifting right towards the products. Good. Next thing, what did you have? Say again? So you added potassium thiocyanate, but the thiocyanate was the species that was the important one, SCN minus. That was our species that was important. Color change? Reddish, right? So we know that it's not like blood red, but it actually does turn pretty red if you add a lot of it. So this was a micro-scale experiment. Which way does it shift? To the right towards the products, and you can see that's because the red color appears. Last one you added in the first trial? So you added KCl, right? But KCl, does that have a species in common with our equilibrium? No. Can K plus or Cl minus react with our equilibrium? Not really. It's not going to cause like a drastic change. It's not going to make us. It's not going to make solids. Not going to make a pure water, pure substance like water. It's not going to make a gas. It's not really going to. I mean, it might be able to combine with one of these ions, but it's just going to uncombine because it's soluble. So what did you guys see? You said it turned clearish, right? And so that wasn't either light brown or red. That was just a dilution factor. And so I heard it. What happened? No shift. No shift. Okay, simply because there's no way for it to affect the equilibrium. All right, the next one was a little bit more challenging. You had carcinogens, and you had the yellow potassium chromate and then the orange potassium dichromate. And you can see this reaction has hydronium in it. But what is just hydronium representing here? Huh? An acid, right? Hydronium is really just representing something acidic because that's what H3O plus is supposed to represent. First species added. What do you guys do? So to what here? To yellow or to orange? Was this the orange one? No, it's yellow. All right, so the yellow one, which was chromate. Oops. To chromate, you added HCl. Okay, so then what color did it change?
Orange.
Orange. Off the bat, you're like, you could tell at the very top it was like a different, like almost layer. It turns orange. So what is that representing? It's shifting towards to the product. So how did adding this make it shift? Say again?
The H.
What do you mean the H?
It's the acid.
It's an acid. So hydrochloric acid is an acid. So what did you technically add to this equilibrium? You technically added hydronium, right? Because an acid spits out H pluses like crazy, right? Well, H plus is hydronium. So you're spitting out, basically, you're adding hydronium. So you're adding a reactant. Adding a reactant has to shift which way? To the right, because it needs to be consumed. You need to use up the reactant. So that one's going to shift right initially. Did you add something back on top of this? Not on this one? Okay. That was the next one, right? Okay, so this one, the orange one now?
No, it's good.
Yellow still?
Yellow, but you add both of them.
You add both of them. Oh.
You add
Oh,
the
sorry.
A.
This is the one. Okay, so this is the chromate, yellow, and then you added HCl, and you said again it turned orange. I think that's the same thing. And then what did you add on top of this?
An AOH.
Then you added an AOH. Okay, so Evan, you got me here. Tell me tell me first of all the color change. After it turned orange, you added the sodium hydroxide. What color did it change?
Turn back yellow.
Back yellow. Can you explain why?
Because it neutralizes the acid.
Okay, so when you neutralize, so we added the acids, those excesses of acid, it shifts to the right. We've got an excess, our hydronium is hanging out. When I add the sodium hydroxide, the hydroxide does what with the acid? And then, but what does it do to this concentration? Right, because after you add the OH minus, the OH chooses to react with that acid, which is going to pull down the concentration, because as it reacts, it diminishes. So basically, we're decreasing our concentration of hydronium. Who cares about the hydroxide? It's not in the equilibrium. But though it's not in equilibrium, it can affect something that's in the equilibrium. And that's why it's important. So it pulls down the concentration of hydronium, so then your stress is like, oh no, I've got what? What's the problem? Not enough reactants, right? Too few hydronium, so it needs to shift back to the hydronium side to make more. And that's why this bottom one is a shift left, where the top one was a shift right. So orange and yellow. The other ones were just the opposite, right? They started with the orange and you added your substances. So then I think you guys can do that. I'll leave that one to you. Let's look at the analysis. Let's do one or two together. Oh, before we do that, let's do our table. James, adding an additional product, which way is it shift? Left, because you got to go away from it. Abby, removal of a product. It's got to shift right, because you have to make more of it to go towards it. Increasing the temperature of an endothermic reaction. Endothermic reaction would be something like A plus energy yields C and D, something like that, because your energy needs to be on the reactant side, because that's endothermic, it's going into the reaction. If you increase the temperature, which way should it shift? Who says right? Some of us are, who's not sure? Okay.
Endothermic is the other one.
Oh, I'm sorry. This one here, my bad. You're like, where are we? I'm going to talk about this one right here, since I just read the reaction part. So, increasing the energy of an endothermic reaction. Which way should it shift? Right, because this increasing temperature basically increases energy, and so you have about too much. You need to get rid of it by allowing it to react, which would push towards a product side. All right, how about exothermic? Yes, it should shift left. So A plus B yields C plus energy. So energy increasing would increase a product technically, and then shift back towards the left side. Okay, addition of reactant species, everybody? Because it needs to. So why are we? It needs to make more products, but that's not really what the reason is. Hold on. Addition of a reactant species.
More reactants. More products.
So there's more reactants than there should be in the ratios, then we need to do what with them? Right, we need to allow them to be consumed and turned to products, right? So it's all about like focusing on the stress. The reactants need to be consumed. Removal of reactant, what needs to happen? It does shift left, but why?
There's not enough.
So the removal of reactant means there's not enough reactants. We need to make more, so we need force production of reactants. Okay, cool. So if you've not finished the analysis, please work on that. 2nd, we did number 1 together of the Le Chatelier's examples. Yes?
Yes.
You do 2, 3, 4. You know where those are. You know what I'm talking about. So you've got those 3 things to work on. Pass up your web quest to Maddie. Pass up web quest to Maddie. My stapler is out of commission. Hold it. And reading guide 18, if you have not finished, if I did not get a check reading guide 18, make sure it goes in the box or it gets passed up to Maddie and I'll sort it out. We have about 20 minutes left in class. Please, please, please work on this. Labs will go in the box whenever you're done. My stapler is out of commission. I might have one more.
Yes, I can be. I wasn't here on Thursday, but I had a few.
Can you put it in the box?
Okay.
I don't know where the stapler is.
I'm just gonna say.
Just fold the corner if you don't have a stapler. Yep.
There's a dog here. Yeah. I have 0 staplers.
Everybody?
Who am I after?
Thanks for being the go-to there.
Does anybody else have theirs? Sure. Just everybody?
Nope. The stapler is not working. All right, you have numerous assignments to do. Thank you.
You finished the lab? How do you know? There's no further procedure.
Well, maybe when you had any blue. Get the color. If the solution starts out.
Oh,
There's that.
what's it? It's supposed to be perfect.
So like the whole solution.
Yes.
The other one should.
Because I'm just gonna say, if it's like the whole thing being heated, then the heat is on the right. Yeah.
So I'm just gonna ask.
I wouldn't know, because that color, you know,
I think that's a and we don't need pictures of it.
Thank you.
Thanks.
to the side.
I don't think you can just say it right.
Oh, yeah.
Excuse me. Thank you.
Yeah, actually, that is the. Yeah.
You're way back.
We don't need a couple. Is that right?
Oh, yeah, that was one.
All right, guys, we have about 12 minutes left. If you can help me pass out a couple papers, that would be great. I'm grabbing this stuff. Okay, sorry. In your lap, each lap first.
Okay, where do you sit?
Right
There we go. Lean up.
Thank you.
Okay.
Yeah, a little bit.
I think it was left.
Okay? Yeah.
It looks like having that.
Alina,
Oh, get up.
are you on number? Oh, Alina. Are we still going to do the tricycle?
He's texted me, he said, "Dude, fill it."
Okay.
It's like you made my week.
Okay, if we are, then I have to my dad bought me one for the concert. I already have one. So.
What? That's what I asked. Probably should have asked. Yeah, they're charging. I know that was. I had
This is not.
You really don't. Is that last time was the last day? I had like 5 last days. This is like yeah, like everything. Looks like
Look, mine's like every cluster. I don't have spread it out.
oh, okay.
I feel bad.
Okay, guys. Who's still working on their lab? Who's still working on their lab?
I think they are the best.
Okay. If you're not working on lab, do not take this purple sheet with you. We have 5 minutes left and I'm using it because I don't like to waste time. Sorry. Not sorry. Not sorry. You can share one of these with a partner next to you, but I want to have some back there. James, Alright, Silencio, and everybody who is not working in their lab, look at this with me. You have about 30 seconds for each question. And just think about it. Yeah, I want to go over some of these. Don't write on it. Do not write on it. And they're this. I accidentally copied the same questions on both sides. Glad I didn't do this in class. Okay. Let's start with number 9. Start with number 9. What does mine say?
Or based on results?
Oh, I don't know. I'm a doofus, guys. I cut them. I cut them the wrong way. I'm a doofus. No, because I'm so happy I didn't do this in class. Woo. All right, let me look at number 1. I'm still on Lena's. Okay. Never mind. So those purple sheets, I'm just gonna
Do you want them back? Just take them. Take them.
just keep it for your own purpose. Never mind. It's never happened. Never happened. So, does anybody else want the other half of the quiz? I don't have two J's. I have two J's. I need one J. Because I know I have a meeting after school today.